In this video, I'm going to be going over logarithmic functions. So first, let's define a logarithmic function. This is what the parent function is. This is the, I guess you could call it the default function. So what does this mean? Well, I can just replace f of x with y for simplicity. For now, this is saying 10, this base is 10, that's the default, to the power of y is equal to x. So this base right here to the power y is equal to x. Similarly, if I have log base 2 of x is equal to y, this would simply be 2, the base, to the power y is equal to x. So a logarithmic function basically is just finding the exponent. Alright, so an important thing to know is what a logarithmic function looks like. So here I have my graph, and we can start plugging in points for the function f of x is equal to log x. And remember, when I'm not writing the base, assume that it is base 10. So this left side is going to be x, this right side is going to be f of x. And we're going to plug in the points 1 over 100, 1 over 10, 1, 10, 100. So what 10 to the power of what is 1 over 100? Negative 2. 10 to the power of negative 2 is 1 over 100. Similarly, 10 to the power of negative 1 is 1 over 10. 10 to the power of 0 is 1. 10 to the power 1 is 10, and 10 to the power 2 is 100. So we can plug in these points. When x is 1 over 100, I'll just say that's here, then the value of y, or f of x, is negative 2. This is not going to be drawn to scale, by the way. Negative 2. So here's where our first point is. I'll do it in blue. And from here, we can sort of sketch out a graph. But this is just the top half. What happens to this bottom part? Does it intersect the y-axis? Does it do something else? Okay, well, let's think about this a bit. We have, I'll just rewrite it, f of x is equal to log base 10 of x. We're trying to figure out what happens when x comes closer to 0. Well, let's just plug in 0, see what happens. Log base 10 of 0. And just for the sake of simplicity, I'll just call this y. This is basically saying 10 to the power of y is equal to 0. Alright, is this possible? Can we do this? 10 to the power of what? Or anything to the power of what is 0? Nothing really, right? We don't have a number small enough to get 0. So we can just say that this is undefined. This means y is undefined. To put it in simpler words, x is just not 0. That's what it is. X cannot be 0. So here we have x is not 0. Now, is there a hole or something? Can it just not intersect the y-axis? All right, we can test that out. We'll test it on values that are negative, x values that are negative. Y is equal to log base 10 of, I'll test the number out, negative 3. This is just saying 10 to the power of y is negative 3. And this, again, does not make any sense, because 10 to the power of what is a negative number? When we raise 10 to the power of a fraction, it's a root. If we raise it to the power of a negative number, it becomes a fraction. So there isn't really a negative number here. So negative numbers, solving for y, if we have a negative number, this requires more knowledge about complex numbers, and I think this is more of calculus than pre-calculus. But here we can see, since x is not 0 and it's not negative, we can define an asymptote for the function of log x. Now, there are also logarithmic identities. First one is the addition identity. If we have log base x of y plus log base x of z, this is equal to log base x of yz. Our second log identity is log x of y minus log x of z is equal to log x of y over z. Our third log identity is log x of y to the power z, can be rewritten as z times log x to the power y. Our fourth logarithmic identity is x to the power log base x of any argument y is equal to simply y. Because we have x to the power whatever exponent of x that gives us y, that's just equal to y. This is just saying x to the power something is y, and this just leaves us with y. And finally, we have the logarithmic identity log to the log base x to the power y of z is simply 1 over y times log base x of z. Let's dive into that. So for this first question, let's just go over logarithmic identities. We'll practice those with numbers. So we are going to add log base 2 of 289 and log base 2 of 729. Well, we can use two identities here. First, we can simplify this left term. We have log base 2 of 17 squared, and this right term would be log base 2 of 27 squared. Now, using our addition identity, we have log base 2 of 17 squared plus log base 2 of 27 squared is simply log base 2 of 17 squared 27 squared times 27 squared. Now we can use our power identity. We have log base 2 of 17 times 27, but we move the exponent to the front. So it's 2 log base 2 of 17 times 27. And this gives us with our simplified logarithm. This problem is asking us to solve for x if log base x of 81 is log base 2 of 16. So this is our numerical part, so we'll just focus on that. Log base 2 of 16 is simply 2 to the power what is 16? 2 to the power 4 is 16. To rewrite our equation, we have log base x of 81 is equal to 4. So x to the power 4 is equal to 81. Well, what to the power 4 is equal to 81? We know that 3 to the power 4 is equal to 81. So x is equal to 3. Okay, so this problem looks a bit more difficult. Solve for n if log base b of square root of log base b of n is equal to log base b of square root n, and b times log base b of n is log base b of bn, and b is not 1. So I'm seeing a lot of log base b of n. I'm seeing a lot of that, and I do not really like that. So I'm going to set the variable a to be equal to log base b of n. Now I can rewrite all my equations. Root a is equal to, well, we can rewrite this. We know that this is log base b of n to the power 1/2. And using our log identity, we have 1/2 log base b of n. So this right side is simply equal to 1/2 log base b of n. So that's just equal to 1/2 a. Now the next equation is b times log base b of n, which is b times a is equal to, well, we can unsimplify this, you could say. This is equal to log base b of b plus log base b of n if we use our addition property. Our addition property right here. So log base b of b is simply 1 because b to the power 1 is b, plus log base b of n, which we said was a, so we have 1 plus a. Now, we can solve the systems of equations, these two equations. So this top equation is looking pretty easy to solve. So we can square both sides. We have a is equal to 1/4 a squared. Now subtracting 1/4 a squared on both sides gives us, or subtracting a on both sides gives us 0 is equal to 1/4 a squared minus a. And now we can divide by a. 0 is equal to 1/4 a minus 1. So we can add 1 on both sides. We have 1 is equal to 1/4 a. So a is equal to 4. Alright, so we have a is equal to 4. Now we can solve for b. We have 4b is equal to 1 plus 4, as we've said here. So this means b is equal to 5/4. So we have a, we have b. We can solve for n now. We know a is log base b of n. So we have a, which is 4, is equal to log base b, 5/4 of n. So this is just saying n is equal to 5/4 to the power of 4, which is 5 to the power of 4 over 4 to the power of 4, 625 over 256.